what do you know about resonance structures? Well, a resonance structure differ only by the placement of electrons. So electrons that can move are lone pairs and pi bonds. Electrons that can't move are typically found on an sp3 hybrid carbon. So this is a big thing. So when students don't recognize this, they put 5 bonds on a carbon a lot of the time. So we want to be careful with our line structure formulas because hydrogens aren't shown, and you want to make sure you recognize an sp hybrid carbon because there'll be 2 hydrogens possibly stuck to it, which you don't see, and then you just draw a double bond on it or stick a lone pair on it, and that doesn't work out so well. So does this molecule here have any resonance structures? And if so, how many? Well, lone pairs can move. Here's a sp3 hybrid carbon. This thing will probably never do anything. So there would be a resonance form of this thing. We moved a lone pair. We moved some pi bond electrons. This carbon could play the game because it's sp2 hybrid. And this oxygen went from being sp2 to sp3. And this probably isn't a major form because we have 2 different charges on the same molecule. We learned that that's not a favorable thing. So on something like this, I'm going to just go ahead, and this one's not going to be as critical as others. But I said earlier, your line structure can mess you up because you might want to stick a bond or a lone pair on a carbon that's sp3 hybrid. And here we see all these carbons look very sp2 hybrid. And so a couple different things that can move. Pi bond electrons. Why don't I just move that pair to start out with? So I could have just moved that pair over there and gone directly to this structure. And here we see we can move 2 pairs of electrons at the same time if we want. Notice nothing came to play over here on this carbon. So here is an example, and possibly don't write this down. Because this is what I see students do. They might say, well, I'm going to make that jump there. I don't know, I'm going to make those jump out. Is this a good structure? Now right here, if I look at that, how many bonds are on this carbon? 5. Yeah, you don't want to do that. So before you start, when we just had the, you need to tell yourself this carbon is sp3. So it can't play. You can't put a lone pair on there. You can't put a double bond on there. If I go around this ring, I see that these are all sp2. This one's sp3, meaning you're never going to put a double bond there. Never going to put a lone pair there. So I can probably make these jump down. Pi bond jump up. So here's the 3 resonance structures we can have. Can't do anything to this carbon. Can't do anything with that carbon. Now when we look at this thing, you should think, man, everything looks like, remember carbocations are very sp2 hybrid. Looks like everything's sp2 hybrid. So I can probably do a lot of moving around of pi bonds. Just start there. I'll put the positive charge out there. So this arrow here is going to bring us down here. That one got us over here. So I don't want to forget about that one there. I'm getting real sloppy. And that one would bring us all the way back up. So we moved a positive charge around. No lone pairs anywhere. Just the movement of pi bonds. So now we have pi bonds and a lone pair and a negative charge. And I think that's all the possibilities. So I'm gonna pretend here. Don't do this. Tell me what's wrong with this structure right here. Right. This one here, you got to recognize from here. Also this one here. All right, so neither could you put a lone pair on there. So resonance structures can explain a lot. Acid, base, acidity, different products and different reactions. What type of reaction does this look like? This looks like an addition reaction. So obviously this has 2 more hydrogens. So if we form an intermediate like this, so here the resonant structures here tell us we can get 2 products. So fun things next semester we'll learn about the 1,2 product and the 1,4 product and how to get make one the major product or the other by reaction conditions. I didn't draw a very good benzene ring. Now here's a benzene ring. Have you seen very many benzene rings in the book that look like this one? Is there anything kind of correct about this that may not be so correct about this? What is the chemistry fact? Which is shorter, a sigma bond or a pi bond? It was an extra credit question. What is what? Yeah, it's shorter. So this is foreshadowing to great things with the benzene chapter. That bond can move there. That bond can move there. That bond can move there. Now I'm going to try and do a better job and make these all equal lengths. And when benzene was discovered, they didn't have X-ray crystallography to figure out that this was wrong. But it turns out every bond is the same distance. So benzene has this special stability where it doesn't undergo normal addition reactions, but it undergoes a special type of reaction called electrophilic aromatic substitution. And notice that is now very sp3 hybrid. Oh, that's the worst. So this thing is called the sigma complex, and it's stabilized by resonance. And then eventually a base comes by and pulls off this electron, and you get the pulls off this proton, and you get your substitution product. So nitration of benzene does this. All right, what is NBS? That's the word succinate in it. But what's important is that it's a brominating agent, and it goes through a free radical mechanism. So I'm gonna put hydrogens back on here. So what we form as an intermediate is a alky radical. So what we're going to get HBr, and that hydrogen with its 1 electron hooks up with the bromine radical and its electron. So this is a special type of a radical because it's allylic. It's on a carbon adjacent to a double bond, and that's stabilized by resonance. So here's 2 different products. Notice the bromine is in the allylic position each time. Now there's probably actually more products than this because I have an allylic proton right there. So if this bromine radical decided to extract that proton, we'd get this. That jumped there, that jumped there. All right, out of all 4 of these products, which would you expect to see the most of? So a review on radical stability. I would say this tertiary allylic radical is much more stable than this primary allylic. So this one here is going to have the way lower transition state going this route. So these are going to be the ones that predominate. All right, so now you've seen about every resonance problem that there is. So probably on the final it will be one of these. And of course on the chapter 6, on the alky halide chapter, we went over that NBS.